Hi, I'm supporting a very exciting program. It's FRANC. FRANC is the foundation required for the computing. As a previous speaker said, a lot of modern computation, machine learning are really limited by the memory bottleneck. And as Dr. Lisa Porter say, and all the innovation has to start from the basic. We have to leapfrog against other competitors. And as Dr. Rosker say, they have multiple waves of the innovation on the microelectronics, and each wave kind of triggered by material and devices in the semiconductor industry. So if we look into what's limiting the current computing architecture, is really built on the decades of the von Neumann architecture, which separate the memory, the computing units by the bus. As the computing load increased significantly to transfer data in a very short time frame, and the bus become the bottleneck, as you heard from the previous program. So in the FRANC program, we try to address this, is to try to think about how can you do the computing directly inside the memory. So how can we do it, is we try to explore more fundamental material. Can we see any new physics, and to give you better memory material, can give us more memory states, like for example, the RAM or the other MRAM devices, or we can use a new memory device property to do even better computation, like stochastic computation or the spiking neural network computation, which can be more energy efficient. So in the FRANC program, we try to address from basic physics material to device, and also some of the enabling architecture to do that. So the program has been started for since last July, and we have finishing some the first phase to study different material composition to give you a more durable pathway for the coming phase. And we have several highlights. For example, like UCA, they've been studying the very low voltage controlled magnetic memory. And also they found out that with this instability in the transient to switch on the MRAM, you can use those transient to do statistical computation, which can give you much lower energy and more robustness in terms of the memory as you average out all the pseudo-random pauses, and to give you a good logic. And then the UIUC, you will hear later, will be building on more mature MRAM technology provided by GlobalFoundries to do the in-memory computation. Traditionally, analog in-memory computation are done in the SRAM or flash, but with the magnetic memory, which is non-volatile, then you can even do more by store the information or the weighting inside the memory near the computing units very closely. So they give you more energy efficiency than Professor Shanbhag from Illinois will give you talk next. Then we also have a Micron to do some study on the different architecture to combine the cross grain and the fine grain traffic, and more efficiently with near memory computation, more in the distributed architecture on a single chip. So there are more performers inside the program. So basically we have two technical areas. The TA2 is mainly focused on new physics material and the devices, and what kind of enabling memory function for the computation will be. And the TA1 is really based on the new memory technology. Can we do the computation at the circuit level, and how the system architecture can be advanced with this new emerging memory technology. So by this, I will pass the talk to Professor Naresh Chen. And he will show you how to implement something like in-memory computation in the technology almost ready for production. Naresh.
Thank you. Good afternoon, everyone. My name is Naresh Shanbhag. I'm a faculty in the Electrical and Computer Engineering Department at the University of Illinois at Urbana-Champaign, and also the principal investigator for our project titled MRAM-based deep in-memory architectures. I want to thank our program manager, Dr. Chen, for giving us this stage to share some of our accomplishments with you. I want to begin first with our team. In the ERI program, one of the objectives is to harness the best from industry and academia. Our team reflects that. We have industry leaders and thought leaders from academia coming together. On the industry side, we have on the defense sector, Raytheon Missile Systems, represented by Mike Birkeland and his team of researchers. Mike and his team are bringing sort of the system integration capabilities as well as system specifications that is driving our research. From Global Foundries, we have Ajay Jacob, Stephen Sauce, and David Brown, who are providing us with the MRAM device, the process design kit, and tape-out services, since in our project we'll be building real-life prototypes of our architectures. And finally, from the university, we have Princeton and University of Illinois at Urbana-Champaign, Naveen Verma, Pawan Hanumolu, and I, and our students. We're all working together to provide this unique concept of deep in-memory architectures, as well as its Shannon-inspired roots, so that we can build AI systems at the edge. And so that brings me to the broader context of our project. Our interest is, certainly our technology can be used in either the cloud or the edge, but since we are driving energy efficiency and latency to its limits, the edge platform is the place where we want to test it out. So these platforms are platforms where data is generated. There's a lot of data generated as we speak, but it takes a lot of energy to process data locally. So today, we have to transport the data to the cloud, extract the model, send it back into the edge device, and then do the inference. If we are able to actually do local processing and learning in the edge, then we can avoid the huge energy cost of transporting data to the cloud. And number two, we sort of alleviate some of the security and privacy concerns that emerge in situations where the edge devices, let's say, taking physiological signals from the individual. Those are very private data, and that's something we want to keep local. However, bringing AI capabilities into the edge device is very challenging, since compute resources are limited. Energy supply is also limited. So how do we pack in, as much as possible, how do we pack in the intelligence into an edge device? Well, we know from our previous speakers, we know that the primary source of the energy consumption in today's architectures, and in particular for AI workloads, is the data movement problem. The fact that even today we are relying on some variant of the von Neumann architecture, an architecture that was proposed in 1945, and we've been tweaking around this particular architecture. This architecture separates memory from processing. So we store data in one place, you have to read it, and then process it in another location, and this very act of accessing memory kills the energy efficiency and also costs a lot in terms of latency. Numbers you can see there, just looking at energy itself, the energy consumption for data access is roughly 2 to 3 orders of magnitude higher than computational energy. Now, this memory wall problem, the well-known memory wall problem, gets aggravated when we are dealing with AI workloads. Why? Because in most of these AI models, machine learning models, they are huge. For example, you might have close to more than 100 million parameters that you have to access, and then make a decision. The decision may be very simple, friend or foe. It could be a binary decision, but still, we have to access a lot of data to get to that point. And so this is the source of the crux of the energy efficiency and latency problem when it comes to building decision-making systems. So a fundamental question that drives our research is the following. We want to design intelligent machines, but we want to operate them at the limits of energy, latency, and accuracy. These three metrics are connected, intimately connected. We cannot talk about one without talking about the other, right? Now, if we were given freedom to synergize, to innovate at the material and device level on one hand, architectures, and then systems and algorithms, what would we do, right? This is the question that drives our research, and I believe this is the question that is indeed underlying the FRANC program. Now, a framework to answer this question was, in fact, put together by some of us in the center called the Sonic Center, Systems on Nanoscale Information Fabrics. This was a center funded under the StarNet program. In fact, Linton Salmon was our program manager. And in this center, we had about 27 faculty and more than 100 graduate students trying to answer that question that I just mentioned. So at the end of our tenure, we had come up with a framework to come up with certain guidelines as to building decision-making systems that operate at the limits. This is a paper that summarizes the findings of the Sonic Center. And one key underlying methodology or the thinking process that we came up with was based on the work of Claude Shannon. So this is, so to understand this and to just really appreciate what we are trying to do here, think of a decision-making machine. It looks at data and makes a decision, where there's a very direct analogy between that machine and a communication receiver. A communication receiver also looks at the received data and tries to infer what was transmitted, right? So both of these engines have a lot of similarities. Fortunately, in the world of communications, the theoretical foundations of transmitting data over a noisy channel, it has been well established. This foundation was laid by Claude Shannon in 1948. And today, all the communication infrastructure in our society are Shannon links. So in our project, in our work, we are asking the question, can we take certain lessons and guidance from Shannon theory and bring it into the design of decision-making machines that operate at the limits of energy and latency and accuracy? Now, one of the lessons that we learned from Shannon theory is that if you have a channel and you want to minimize the energy per bit, you've got to have the channel be a low SNR channel. That is, the channel has to make errors, and then we need encoders and decoders to correct those. So in this framework, we use metrics. We don't look at data as data, but instead as the question, what sort of information content resides in that data, and how do I preserve it as it progresses through a processing pipeline? Second, we look for new low SNR fabrics that allow us a very nice energy efficiency versus accuracy trade-off or SNR trade-off. And third, just as we have encoders and decoders in a communication link, here we look for statistical error compensation techniques that will allow us to push the signal-to-noise ratio of the circuit or device fabric as low as we can push it, all right? And if we take this sort of a very interesting and transformative concept and we apply it to the problem of the memory wall or the data movement problem, we get what is called a deep in-memory architecture, or Dema. So in FRANC, and this is why in FRANC, we are taking a new device, a device that is non-CMOS, MRAM from Global Foundries, but instead of using it in the context of a von Neumann architecture, we are inserting it in the context of a deep in-memory architecture with its Shannon-inspired roots. And then we'll come out with prototypes and boards and software libraries to make it usable. We are providing those, and our intent is to provide those to Raytheon so they can do some system-level testing at their end. We're also getting specifications right on from day one we are being told what the typical DoD workloads are, what are the specifications, so that we move forward in a very informed manner. All right, so now drilling a little bit deeper into the deep in-memory architecture, it is an architecture which recognizes that a memory access is very expensive. So why not, when we start the memory access, we compute functions of data. Instead of reading data, why don't we start from the beginning to start computing functions of data? And how do we do that? Well, we activate all the rows and all the columns at the same time. And so what comes out at the periphery of the memory array are sort of a function of all the data that was stored. And since we are the designers, we can control and sort of target what those functions are. We can make them AI functions, all right? So we aspire in this architecture to have a one-shot, let's say as an example, a one-shot matrix vector multiply. And we process the results of that. We want to process the results in such a way that when we go from analog to digital, in fact, deep in-memory architecture is intrinsically analog for this very reason, that we are packing a lot more bits in the same voltage swing that a typical memory would pack only one bit in, all right? So we are, this is indeed a low SNR fabric, and you can see that it is also per unit computation, it's going to be a lot more efficient than a conventional von Neumann architecture. Now, this is a very radical concept, and of course, we want to verify and validate that it will work. And so in the past, we have, in fact, built multiple SRAM-based Dema prototypes, both at Princeton and UIUC. And through various, for different workloads, we have shown that one can achieve, I would say, close to about 2 orders of magnitude reduction in the decision-making energy delay product. So these are not, we're not talking about max. We're talking about a machine that has to make a decision. If you use deep in-memory architecture, what is the energy delay product of that decision-making process for the von Neumann architecture and for ours, and we get these kind of numbers. So therefore, in our project, in the FRANC project, we are asking the question, what if we use MRAM? And what sort of, if we change the device, what sort of benefits can we get out of it? What sort of numbers can we get out of it? So why MRAM? Number one, it has higher density than SRAM, and so we can pack a lot more functionality in the same unit area. Second, it is non-volatile, so which creates a possibility of having ultra-low power operation, since we can duty cycle the computations and the tasks. And third, as we heard from Tom this morning, it is a device that is available for their customers. It's in production. So that gives us, as researchers, an opportunity to actually build real-life prototypes, right? So it's beyond CMOS. It's a non-CMOS technology, but we can build real-life prototypes. Now, having said that, there are a number of challenges that MRAM imposes on the design. In fact, a lot of these challenges, most of these challenges are very difficult to overcome if we were sitting in the von Neumann world. But when we move into the world of deep in-memory architectures, we have ways to overcome these challenges. In simple words, the MTJ device has a very high conductance, so very low resistance. And furthermore, the high and low values of the resistances are pretty close to each other. Furthermore, there's variation. So high resistance and low resistance, they vary with each other. They vary across the die. And so you sort of see that the MRAM device is a naturally low SNR type, can be used in a low SNR fabric. And if you were trying to suppress that, the noise, and trying to build a high SNR von Neumann architecture, we might run into energy and delay problems. Now, understanding the MTJ device, we had a lot of help from Global Foundries. And over the last 6 to 8 months, we came out with 4 different Dema architectures, deep in-memory architectures. And 2 of those we have selected for prototyping. These all 4 architectures, in fact, address those challenges in different ways, all right? But the ones we have selected, they have something in common. Number one, they are single-shot matrix vector multiplications. Of course, there are differences. In one case, we might be using a particular kind of a bit cell. where bit line and source lines may be parallel. In the other case, we have bit line, source line being perpendicular to each other. In bit line sensing or Dema BLS, we will be sensing the bit line voltage. In case of Dema CDTS, current drive time-based sensing, we are sensing the source line current. In one case, we may be using voltage mode conversion from analog to digital. In the other case, we are using time-based conversion from analog to digital. So these are all different options that show up very nicely once we step away from the von Neumann style of thinking and think about these deep in-memory architectures. And finally, both of these architectures have something in common. Number one, the last point I want to make here is that in both cases, there's a very, very clear SNR versus energy efficiency trade-off. And this is the trade-off we are looking for, since Dema has a very strong Shannon-inspired roots, and we want to exploit those roots. So using the PDK, the process design kit provided by GlobalFoundries, we have built schematics and layouts, and then we have estimated, these are all estimates of the potential gains in energy delay product. It includes all the peripherals, the driver circuits for the word line drivers, the bit line drivers, and the readout circuitry. So all of the overhead of the peripherals have been included. And we get some really nice numbers, between 2 to 3 orders of magnitude reduction in energy delay product, similar to what we had seen in the lab with SRAM prototypes. So here, the big question for us right now is, let's see how much of this we can get with our MRAM-based Dema prototypes. Right. Now, the numbers that I just showed you were, in one sense, conservative. Why? Because this is our first design, and just to be careful, we have not really pushed the limits of the signal-to-noise ratio. Right? The numbers that I just showed you came about because we moved from the von Neumann world into the world of deep in-memory architectures. Simply because we are never reading data from memory, we are instead computing, they're instead processing or reading functions of data. That switch, that change in perspective gave us those numbers. Now, moving forward, we're asking the question, let's now push the limits of signal-to-noise ratio of the device and circuit fabric. And when we do that, let's then come up with statistical error compensation techniques so that the system becomes reliable. Even though the circuit fabric may be low SNR, the system is making very accurate, highly accurate decisions. Right? So we have come up with 2 methods for enhancing the SNR of the deep in-memory architecture circuit fabric. One of them is from Princeton. So Naveen and his students have built this, come up with this approach where, consider a deep neural network. We know that we can train them today using SGD or stochastic gradient descent algorithm. And that algorithm learns the statistics of data. But since we have the statistics of MTJ variations, which we get from the process design kit from GlobalFoundries, we have a distribution of MTJ variations which can be sampled and then injected into the inference path of this training process. So now the same algorithm is actually learning not just data statistics, but also the statistics of the underlying MRAM-based circuit fabric. Right? And as a result, we show that the model parameters that this learning process generates is able to compensate for very large or very high levels of variations. And this is what we are looking for. We are looking to make reliable decisions in presence of low SNR circuit operation. The other approach is from UIUC, University of Illinois. It takes a very different path to enhancing the SNR. It uses coding, and this is an example of a fast Fourier transform. And FFT is a very important kernel for Raytheon since they build radar-based systems. So one of the things we did here was to find ways to reformulate the FFT algorithm so that it can be mapped efficiently onto a deep in-memory architecture, number one. And once we do that, then we figured out a way to pre-distort in an efficient way, pre-distort the coefficients of the FFT so that when the MTJ variations are present, as the input propagates through the architecture, you get a very high quality, a very high SNR at the output. So without using this technique, you can see in this plot that achieving a high SNR of roughly 61 dB is difficult because we are limited by MTJ variations. But coming out with using this particular right time compensation technique, we can boost up the SNR by another 18 dB or so. So it's very promising. These two techniques are very, very promising. It tells us our next design, or in the future, when we build our next Dema chip, we have these two tools that we can use to enhance the energy efficiency further. All right, so the current status of our project is as follows. The two Dema options that I talked about earlier, they have been taped out. So just last month, end of June, these two have been taped out. Currently, they are being fabricated in Global Foundries, Dresden, Germany facilities, the 22 nanometer CMOS part of it, and then it'll be shipped to Singapore, their facilities in Singapore for integrating MRAM in the back end of the line process. Hopefully, in the next few months, we'll be able to report some testing results. Second, the models of these architectures, we have shared it with Raytheon, and they have done internal analysis of what they call as the system impact, the impact on mission lifetimes, for example, of having these architectures as part of their system. And then finally, we've already started the technology transition activities within the project. We have from Princeton, Naveen's group has their SRAM-based chips with boards and software libraries that allow an application designer to write applications for a Dema architecture. So that sort of activity is already going on with engineers from Raytheon working with Princeton researchers. All right. So with that, I want to talk briefly about next steps. Our current designs, the ones that we taped out, are our first designs, and deliberately we have made them single bank designs. As we look into the future, we want to scale up the complexity of our designs. We want to make them multi-bank with appropriate system interfaces so that a diversity of applications can be mapped onto those architectures. We'll have chips, we'll build boards, and then we'll work with Raytheon in testing those out. So that's one vector that we plan on following. The second is deep in-memory architectures with MRAM is actually a very interesting, it created a very rich area of research for us. There's lots of very interesting design techniques and design guidelines and design methods that have been discovered. So since Dema is a very regular architecture, we believe that it's possible to encapsulate all of that learnings into a sort of a platform design tool or a platform tool that will synthesize MRAM-based Dema architectures. And that way, a designer could use it and very efficiently generate these designs. So these are sort of two major vectors that we see occurring in the rest of this program. So at the end, I want to summarize by letting you know what our mission is. So as you can see, we have set up very ambitious goal of achieving close to 2 to 3 orders of magnitude reduction in the energy delay product of decision making. And we are doing that for DoD workloads that we are obtaining from Raytheon. We are using Global Foundries MRAM device to demonstrate these ideas. And from the university side, Princeton and UIUC are providing the design technology, deep in-memory architecture with Shannon-inspired error compensation schemes. So in this way, you can see that our project is a full stack approach from devices to architectures to systems. And this indeed is the objective of the FRANC program, to think of new novel compute paradigms by synergizing across the 3 domains. So with that, I thank you for your attention,